Okay, I hope you can see this.
Yes, sir.
Okay, good. So, just to go back right to the beginning, we gave a brief introduction to granular materials initially, and then we started talking about tools. The first thing we did was vectors and tensors, and then I told you about some programming for hard particle simulations and soft particle simulations. Now, those are simple programs written for frictionless particles in 2D, but there's a really great open source software that is available called LAMPS, which we can use to simulate granular flows very easily. And I think this is really where I want you to sort of concentrate. The first two things that I told you about, that tells you what is inside a program like LAMPS. We can also write something like LAMPS, that's not a problem. The only thing is that, as you go to larger systems, you would like to make the programs run in parallel. That is, they'll divide up the computation into small parts which run on different processors if you have a multi-processor system and so forth. So all those things are taken into account into LAMPS. So today I want to give you a brief introduction to LAMPS. In the previous class, we saw that one of the important things is to get computational efficiency in getting the neighbor list. And one way of doing it is to divide the domain into bins, and then if your particle is in this bin, then look at only close bins and then find, because we know how to put particles in these bins using something like this. And then we know how to store it also quite efficiently using these two matrices, head and L list. And this essentially contains the particle number of the last particle added to the bin, and L list is the list of particles in each bin. And this L list is very interesting because if you put in L list of IP, where IP is a particle in the bin, then the matrix will give you the next particle and so forth. And you can keep doing that until you reach 0 when the list ends. So using this, you can get the list of particles in a bin given any one particle in there. And head of cell tells you the number of one particle. So we saw all this last time. And this is all part of any good code for doing either hard particle or soft particle simulations. And all of this is included in this program called LAMPS, which stands for Large Scale Atomic Molecular Massively Parallel Simulator. So it actually is been designed for molecular dynamics. That is, you actually want to simulate how molecules move. But essentially, particles can be thought of as molecules, but with different types of interactions. So molecules will have certain force fields with which they interact. We have our Hertz equation and so forth for particle-particle interaction. And here is a sort of, what I've shown here is essentially a snapshot of the website for LAMPS. And if you go there, you'll see, all sorts of things that it'll tell you what are the features, what are the packages, and all this available. You can download and install the code from various places. And this is really very useful. And this is extremely well written manual. So given any command, it'll tell you exactly what the command does and how to use it. So this is something that, I never, even now when I use any command, I will just go there and check that am I doing everything correctly or is there something that I have to. And then various other things and the tutorials and so forth. So what is lamps? So if you see, this is really, oh, I think excuse me, I think I have the wrong file here. One second. I think that I had updated this file and I wanted to tell you a little bit more about lamps. So. Yeah, this is it. So this is what lamps is. So it's a molecular dynamics code, and you can simulate all these things with millions or billions of particles. It can run on a laptop or desktop or even on a parallel computer. And for this parallel computing, it uses something called MPI, which is the message passing interface. So this is again another open source library that all the computers will usually have. And this whole code is written in C++. It is free and open source. That means, you can download the code and you can see exactly what is inside it. So you'll be able to see whatever I have taught you in the previous classes, you'll be able to see all that in here. And it's designed to be easy to modify or extend. And you can put in different force fields, atom types, boundary conditions, and so forth. That's easy to do. So what does it do? Like we have seen, it just integrates Newton's equation of motion. And you can have various kinds of particles. They can be atoms, molecules, electrons, coarse-grained cluster of atoms, mesoscopic, macroscopic clump of material, whatever. But one of the things that's very important is neighbor lists. It uses neighbor lists to keep track of nearby particles, and these are optimized for systems with particles that are repulsive at short distances. So that's like what we are doing. That particles have no force if they don't touch, but only at short distances when they're touching that you have strong repulsive forces. And on parallel machines, LAMMPS uses spatial decomposition techniques to partition the simulation domain into small subdomains of equal computational cost. And each subdomain is assigned to one processor. So, you imagine you have a volume and you have 4 processors, then you'll just divide it into 4 volumes. And then each of the computations is done in parallel on each of those on each of the 4 processors separately. And how do you use lamps? Well, what you need is a script file. So this is actually just a list of commands that you put down, which lamps understands, and it will, through that you can do the initialization of your system. You can define what sort of particles you're using, what sort of other settings you have, like boundaries and so forth, and then for how long you want to run it. And typically, the command to run it, let's say once you've downloaded it and everything, it will be something like lmp -in and then the name of the script file. So this is if you're not running in parallel, but if you want to run in parallel, then the command is mpi run -np4. That means you run in parallel using 4 processors, and then you give lmp -in script file. So this is the name of the file that you should use. Okay. Now, uh, this particular command lmp, in some of the places, it may be LMP underscore serial, or in here it may be LMP. The serial means you're running only on one machine or one core. And if you're running on multiple cores, sometimes you have to write LMP underscore MPI. But in the newer versions of lamps, you just have to put in LMP. That's enough. Okay, so the basic point is this is a very powerful code, but the commands to run that code are quite simple. Okay. And here is one example of what a script file looks like. So this is just a text file. Any question? So, okay. This is the script file, and you'll see that the first line is units. So you can specify the units. Here I'm using CGS, that is CGS units. What type of atom? So when we are dealing with, particles, we should simply write sphere over here. So this is usually fixed. Now, what about the boundary condition? So what we are saying is that, let's say if we have a box of this type, then this is one boundary, this is the other boundary on the other side. And so if this is the x direction, then the first f means that you have a fixed boundary in the x direction for both of them, both the surfaces in the x direction. You also have a fixed boundary in the y direction, and you have a fixed boundary in the z direction. So this is something that is can be changed. And the other kind of boundary condition which we'll see, and I'll explain that later, is that you could have periodic boundary conditions. So in that case, instead of F, you write down P. Again, what I would say is that, one can just go and look. Now say, okay, here I have some doubts about this boundary. So what I can actually do is I can simply go to uh, the lamps manual, and I'll just show you that, and look at the command boundary. Okay. And this is what it looks like. This is what the manual looks like. So you can see there are all these commands, but here is the boundary command, and it will say that, okay, boundary XYZ. XYZ is equal to P or S or F or M. So P is periodic, F is fixed, S is non-periodic and shrink wrapped. That means the boundary will shrink to, so that, it just about keeps all the particles inside the boundary. M is non-periodic and shrink wrapped with a minimum value. So that means the boundary will actually shrink in size to encompass all the particles, but it will not shrink below a certain value. And so you can put in things like this. You can have PPF or PFS. So this will be in the Y direction, you can have two different types of boundaries. One is fixed, the other is shrink wrapped, and like this. And then you can see that it's given in detail. What does each thing mean? Okay. So this way you can easily set your boundary conditions. Okay, so now let's go back to this thing. You can see this now. This is our script file. So we had come up to boundary. Then you have to define actually the region in which you want to do the simulation. So this is a box. That means it is of this type of shape. And these are the dimensions. Now, since we have used CGS units, these are the dimensions in centimeters. So this is 0 to 20 centimeters in the X direction, 0 to 1 centimeter in the Y direction, and 0 to 20 centimeters in the Z direction. And to correctly put everything, in the coordinate system we are using, this is X, this is Y, and this is Z. Okay, for these examples, this is how it is. So in all of them, we are doing like this. So this is the X dimension and the Z dimension. So that is 20 by 20. And in the Y direction, the thickness is just 1 centimeter. Then once you have defined this, then you have to say create box, one box. One means how many types of particles you have in there. We have only one type of particle, that's why it's one, and box. So this tells the program that this is the simulation box. You can create many other regions within that also, but the name of this region is box. You have to name those other regions something else, and then you can use that for computations and other things. Then the next command is read data. So this is telling you all the data. This gives the data file, and the data is in this file called position velocity dot data, and then you say add append. So then whatever is in this gets put in here. So now once we have defined the box, we want to put in all the particles in the box. So this, by reading data and writing add append, it will put all the particles in the box. Then this says how will the particles interact. So what we say is that these particles are frictionless and they follow the Hooke law. So that's why this is what we had defined as Kx. This Gn is the same as Kv, and this corresponds to a coefficient of restitution of 0.9. But there's no tangential forces, so Kt is 0, Gt is 0, and the mu, which is the friction coefficient between particles, is again 0. So again, you can go to the manual and look at exactly what are each of these and what is the formula used for calculating the force. But this defines the force between the particles, and we are using a linear spring, just like we used in all the other examples before. And then you get this, which says that this pair style is used for all the particles. So there's only one type. So star means star and star means between all particles of all types. Then we specify the time steps. So this is the time step in seconds. Then this gives us what is the boundary condition. We have said that the boundary is a fixed boundary, but when the particles come to a boundary, what should they do? Well, they should just reflect. So both X, Y, and Z. X low means the boundary closer, and this is high means the away boundary, and so forth. And all of these are reflecting boundaries. Then this essentially says how to integrate it. So this is saying that you have to integrate for a sphere, keeping the number, the volume, and the energy fixed. We'll always use this type of command, NVE. Other possibilities could be NVT. which is keeping number, volume, and temperature fixed, or NPT, which is number, pressure, and temperature fixed. So when you're dealing with atoms and molecules, those may be useful, but for us, we'll use just this where energy is held constant. And then this is just a command which says that the velocity, when you have, let's say, periodic boundary conditions sometimes, so it's not very relevant here, but the velocity information should be shared. Then these commands dump and so forth, these are to write out the data at every time step. So it says write the data for all the particles in a custom way according to what we have written here after every 1000 time steps in a subdirectory temp, and the file name is called out.dat, and the star will tell us what is the time step over there. And here 6 means there will be 6 numbers over here. So it will be 0, 0, 0, 0, 0. So 6 zeros will be added. And then if it's the first one, it will come 1, 2, 3, 4 like that. And what to write in the file? You write down the X, Y, Z position, Vx, Vy, Vz position, and the identification of the particle. And then, so this is just a way of what this dump modify command, it just specifies the format of the output file name. This just says to write out, the time and kinetic energy after every 200 time step. Now, the particular way of integrating this, we say is this Verlet. We didn't look at that, but just like we have the predictor corrector method, this is another way of calculating the, doing the integration of the Newton equations. And this is a very efficient way of doing it. And I'll show you in maybe the next class what that formula is. And then how many steps to run. So we want to run 89,000 steps at this time step. So we'll go up to a time of 0.89 seconds. Okay, so this is actually the program box 1. And we've done this review of commands. And so I'm going to do this first example. I'll show you this read data file. Then do a demo of this. And then there's a log file and we'll look at that. We've been using this GNU plot, but I'll show you also another thing called OV2. Okay. So now let me just show you a few demos, and for that I'll go back to the computer. Okay. I think I don't need this right now. Okay. So I'm going to share my screen. Okay. Can you see the entire screen? Okay. So now here is the program that I just discussed. It's really simple. Now, what I do first is that I'm going to show you first the initialization file. It's just like what we had in the earlier examples that we did, but I'll just go through it one more time. So this is the C program called ini.c. These are some of the definitions. This is a small sub program inside here which calculates a random number. So it returns a random number between -1 and 1. These are some constants that are used by the random number generator. Then you open a file called par.box, and it reads the number of particles, the length of the box, the coefficient of restitution, and the maximum velocity. This is the random number seed. This is the density of the particles, so that the mass is equal to 1, and the diameter of the particles is taken to be 1. So this is how we had made everything dimensionless. So that's how we do it. So these are all the positions, how to calculate. You start initially with x to be sp2, y to be sp by 2, and then you can do the velocities also like that, random. And this puts all, if you go through this algorithm, it will put all the particles on a grid, and each is given a random velocity which goes from plus Vmax to minus Vmax. So it's Vmax times ran 0. So once you generate all these things, then you have to write it in a specific format that LAMMPS can understand. So I create this file called pausewell.dat, and the header is this, and then it says number of particles, then it says you have to say so many particles are there, and then so many particle types. So there's only one particle type, and n parts we have already seen, blank line, and then this is the size of the domain, 0 to L, 0 to 1, 0 to L. L is 20 in our case. And then you put down the particle number, you put down the mass of the particle, the diameter of the particle, the density of the particle, then the x, y, and z positions. So the y position is always 0.5, and these are the rotational velocities, again 0, 0, 0. And then you write down after that all the velocities. So the particle number, then Vx, Vy is 0, Vz, and then again angular velocities. So this is how you write the initial program, and then when you run it, so when I say I create an executable called ini and I run it, so it creates this file called pausewell.dat. And if I look what is inside this, you see, as we had written, this is the number of particles. The initial time is 0. There are 25 atoms, one atom type. And the x low, x high are 0, 20, 0, 1, 0, 20. And then it tells you for every atom or every particle, this is the particle number, the mass, the diameter, the density, x, y, and z. And similarly here, it gives you Vx, Vy, Vz. So Vy is 0 for all. So this is what it is. And if you want to see this, you can open this using a software called Ovito. So Ovito is a very nice open source visualization tool. And you can again download this, and you can see all the particles here. So there are 25 particles in a box of 20 by 20. And this is just showing the different views, top, front, side, and a perspective view. Okay. And here it has got some features also. You can put in some color coding. So if you want based on velocity or whatever, you can decide on some things, whether it's particle radius, density, position, and so forth. But let's say put Vx, If you put Vy, then all will be 0. And Vz, again, you'll see they're all random. Vx and Vz are random. Okay, so Ovito is a nice way of seeing this stuff. So then once you have this done, then you can execute. So that means now I've created this initial file. This is what is read by my command box1. So I can say lmp serial minus in box1. So this is what is the command that will run lamps, and that's it, it's done, because we are running for a very few number of particles. And so this is what happened, and this is giving us all the times and so forth. So if you see, I just said lmp serial here, and then it ran the job, and then it gave all these things. And one of the things that I always read is total wall time. So how much time did it take to run? Well, according to this, it took 0 time to run, which was, felt like that. Now, what you'll see is that when the program runs, then it generates this file, which is the log file. And in here, you'll see everything. First, it puts down what is the script file that you've run. And then it gives you all these things, and then it tells you time and kinetic energy. How does that change? So you can see this. So I've run it for a very short time, so it only goes up to the first collision, and then I'm trying to do essentially the same thing that I had done in the earlier sort of I'll just do exactly what I did for the other codes. So now I've run it, and what it does is, and I'll show you one more thing, is there's this directory called temp. So all the data that is generated, the position, velocity, all this data is uh, stored in these files. So this is written after every 1,000 time steps. So the out 0 is the initial, then after 1,000 time steps, 2,000, 3,000, and so forth. So again, you can go to Ovito, and you can just go to this temp file and then open the first file, and so you can see this. And here you first go to particles and see the particle radius is 0.5 in our case, so then it will give you the right answer. And then again I can add modification, and here we have done this, so here I can put it as Vx. So this is the x velocity of all the particles, and then I can just say play. So then it will tell you how all the particles are moving, and you can see the particles are moving slowly, and there. So let's say I'll not put color coding. So then the particles, you'll be able to see them move again. So I'll start it again. So we started here, and you can see they're all, since they all have random velocities, they're all moving, and they're all moving at the same time step. And these two particles, which is 18 and 19, they are the ones which we saw, they will collide first. So this is, I've taken it right up to the first collision. And of course, you can see this in sort of magnified views and all this kind of stuff using Ovito. So you can see the, the two particles coming and how they collide. So they are apart, and then I bring them together, and you can see that there the collision may have just started, and now it's finished, over. Just remember, I'm writing at every 1,000 time steps. So between any two images, there are 1,000 time steps. So you see everything in great detail. Okay, so now you can use Ovito to visualize, but also you can visualize using GNU plot. So I'll just copy over the initial file. So this is the file which is at time t equal to 0. So you can see there's all this initial stuff over here. And so I need to just delete those things. So I'll remove that initial. Okay. So we have this one file called pause.p.dat, and then at the point of collision, we know that after 87,000 steps, there's a collision. So at the point of collision, I'm going to copy over that file. And I'll call that as pause.dat. And if I again basically, I want to just get rid of all these initial text files so that I can plot these. And then I'm going to copy this over again. To another file called call1.dat. So this is just to see that, okay, I want to plot only the positions of the colliding particles. And again, I will just edit this. This has all the particles, but I only want to keep the positions and velocities of the particles 18 and 19, which is why I'm deleting all the other data. We know 18 and 19 are the ones that collide. So now I'll be able to do exactly what I had done earlier. Now I'm using a program called GNU plot for doing this. This is also a nice way of plotting things. And this is the website of GNU plot. This is again also a free and open source software you can use on any platform, Linux or Windows, Mac, anything. and it's really very powerful for plotting. So you can have a look at this. So I've created some files, so these are files in which I can plot all of this data, and it plots these circles and all for the particles at different positions and things like this. So if I do GNU plot and I do PL ini, so this is the initial data. This is like what I had shown you. I've shown you 100 times already. This is the XY positions of the 25 particles. Now this is the vectors for those particles. This is the velocity vectors, which you can easily do in GNU plot. And then next I'd like to just show you what happens in the collision. So that for that I have another GNU plot file called box1, and it shows you all this. So it shows the initial position and it shows the position of the particles after collision. That is, at the point of collision, these two particles are going to collide and they will go in that direction. And this is the position before and after. And finally, if I do this PL check, then there's a comparison it makes. So you can see this is the two colliding particles, and the green arrows are what you would get from the hard particle simulation. So you can see that there's small differences, but they're pretty close. Okay. So this is for how you would use lamps and so forth. And if we go on, so here we have another I'm going to just try running this. So now here I'm running for a longer period of time, more particles. So it took a little bit of time. So you see wall time was 1 second. Previously it was 0. Now it's coming 1 second. And now if I just, these are the initial velocities. This is the velocity after some time. And here I've taken the coefficient of restitution to be 1. So as before, you have a constant kinetic energy because these are. Now the next one I'm going to run, that was with a coefficient of restitution equal to 0. So the kinetic energy remained constant. Now if I run again it took about 1 second. Same thing, exact same thing. Only thing now I've taken a coefficient of restitution which is slightly lower. So you can see already that the velocities have reduced and the kinetic energy is coming down. And we can again see what happens very nicely using Ovito, because I can go back to this, go to here, go to temp, and if I open this, here are all my particles. I can put in my velocity. So this is the x velocity, and we'll see that as time progresses what happens. You can see how the particles are all moving. It's it's not as if the particles are jumping, but what is happening is that every time there's a collision, the velocity suddenly changes. And so it feels like, the particles are jumping around. But if we don't have the color coding, then you'll see that the particles are moving in a nice smooth way. But they're colliding with each other and they're slowing down a bit. Okay. Any questions?
Sir, in the previous simulation,
Huh.
the abrupt color change was due to the velocity change, no?
Correct.
Yeah, yeah. Okay, okay.
As soon as it collides, the velocities suddenly become from plus, they become minus. So then suddenly it goes, the color change becomes. And since we don't see it smoothly because we are plotting after every 1,000 time steps. So in 1,000 time steps, the collision will be over. So you see the velocity before collision and then after collision. So suddenly there's a change in velocity.
Yes, sir. Thanks.
And then we can do the same thing with gravity. So I think that's called run G. So again, it's running, and this ran for 4 seconds. And here is the initial. This is the initial vessel velocities. Then this is what happens after a long time. With gravity, it has just settled down, and the kinetic energy has just gone to almost zero. And I can do again with Obito, and what you'll see is I open this. This is how it starts, and you can see the particles are just falling down under gravity, and then they just slowly settle. So this is highly dissipative. So it's for all practical purposes now the velocity is just zero. What is nice over here is that really you can do such powerful calculations by just doing some very, very simple uh, very small simple changes in the programs. So the first one, like where the coefficient of restitution is zero, all I have to change is I put gn equal to zero. If gn is zero, that means essentially kv is zero, so coefficient of restitution is 1, and the rest of the program is exactly the same. Now if I look at box, which is there, the only one number is changed, 148, and now you're doing that whole simulation again, but with a coefficient of restitution equal to 0.9. And in box G, everything is the same. All I do is I add one more line. It says this fix, fix means it adds some constraint to the system. So all I've done is I've added one line which says fix, and this is the number of the fix 3 for all particles. Put a gravity of 981, and the gravity acts in the direction of the vector 0, 0, -1. So it's acting in the minus z direction. That's why all the particles went down. If supposing I did this, what do you think will happen? Now the vector is pointing in 0, 0, 1. So it's pointing in the plus z direction. And now if I run the same program, run G, that means run with gravity. So you can see same thing. But now all the particles are sticking to the top wall because the gravity is acting in the upward direction. You can see this in here also. See the particles, because gravity is acting upward. So that's how we are doing it. And you can do, let's put this back so that next time when I run it, some strange thing doesn't happen. So I put it as, let's say, -1. Supposing I put this as, I can put the gravitational vector in any direction. Supposing I put as 1, 0, -1, what is going to happen? So I'm just running it, I'm not doing everything else. And let's look at it under Obito again. So now I've changed the direction of the gravity. It is got 1 unit in the x direction and 1 unit in the -z direction. So they'll come down, but they'll also be pushed in the x direction. So when you do this, you see how it's going. So the gravity is actually acting in a 45-degree line like this. So, physically what it means is that your box has been tilted by 45 degrees and the particles are now falling in down at that angle. So I just wanted to illustrate, that it's really very powerful. You can do all sorts of things, and it doesn't, I mean, you don't have to do huge programming to be able to do these kinds of calculations. So, now I've kind of shown, and I'm going to show this in the next class, maybe explain a little bit more. So this is for another kind of system, which you can see has reached steady state. And if I show you on Ovito, this is example number 3. So you can see here, there are some particles over here which are in some random fashion, and the rest of the particles are up there. And if I play this, you see this is fallen, and so you can see that the bottom particles are stationary and the particles on top, they are flowing. And as they go out of here, they come in from the other side. So, we are simulating essentially shear flow on a plane, a shear flow on an inclined plane, because here the gravitational vector is not acting downward, it is acting at an angle like how we saw in the previous example. So you can see that you can generate flow also. So how do we do that? I'll show you in the next class. Okay, so with maybe in the next class I will finish off what I want to say about using lamps. What I would encourage you to do is please have a look at the LAMPS website and try and see if you can download it and try and run some of these programs that I have put up on Moodle. And I think that in the next class I can answer any questions that you may have on those things. So with that, I'm going to end the class. Thank you and see you tomorrow morning.